Hello everyone, I'm sure that you enjoyed the previous talk by Dr. Siuma. She taught all of us about the second price auction and the fact that it is a dominant strategy, weekly dominant strategy for everyone to bid his or her valuation. So if I value the object for $100, namely I'm indifferent between buying or not buying at $100, then I should bid $100 and probably I will pay less because I paid the second highest bid. So and by the way, that result is nothing to do with any attitude to a risk or it is if it is finite number of let's say if the value of the object can take finite values or infinite values, no matter if it's the optimal strategy for or the weekly dominant strategy of every bidder is to bid his or her valuation. Now I want to move to the first price auction. This is much more complicated. First of all, let's notice that while bidding my valuation, which is called bidding truthfully, while it is a dominant strategy in the second price auction, it is dominated strategy for the first price auction. Why? If I bid my valuation and I don't win, I get zero. If I bid my valuation and I win, I get zero. Why? My valuation is V minus the price. If I bid V, it's zero. So that guarantees that my payoff will be zero no matter if I win or not win. Why shouldn't I reduce it? Let's say my valuation is 100. Let me bid 80. If I don't win, I get zero like the other case. But if I win, I make 20. So bidding below my valuation is always better in the weak sense than bidding my valuation. So it's really opposite. In the second price auction, it is weekly dominant strategy, while in the first price auction, it is weekly dominated, nonsensible strategy to bid your valuation. So what should I do? First, I would like to tell you there is no weekly dominant strategy for the first price auction. And if we don't have dominant strategies and we cannot solve the game by successive elimination of dominated strategies, we have no choice but to go to use the Nash equilibrium concept. So my question, what is the equilibrium bid of a first price auction? Okay, so let's say we start with result 2. The optimal bidding strategy in a first price sealed bid auction is exactly the same as in the Dutch ascending auction. In these two auctions, bidders do not have a dominant bidding strategy, and the equilibrium strategy is usually very complicated to compute, as it depends, unlike the previous case, on the beliefs about the bidders, about other bidders' valuations of the object. So even if I know that my valuation for the picture is $100, I have no idea about what is your valuation. So I have to have some beliefs. I think it's closer to 70 than to 50, or maybe everything can happen with equally likely, with the same probability. In any event, my equilibrium strategy really depends on the beliefs of each one about the valuations of all others. Quite complicated. Sometimes you have some vague beliefs. We'll talk about it. So the general bidding strategy is, and this is a theorem. First I read it, then you'll realize that you don't understand what I'm saying, and that will be my job to make you understand. So first, what is the result? The equilibrium result is as follows. It's in the red. Bid your estimate is like an average or expected value of the second highest valuation among the bidders, assuming yours is the highest. Okay, what does it tell me? It tells me the following thing. First, think what is your valuation. My valuation, let's say, is 100. Then estimate what is the highest valuation among all other bidders. This will be a second highest valuation because I'm the first. I'm the highest. So I have to think. First I have to know my valuation, but I also have to think, well, what do I believe about the second highest valuation or the highest valuation of everyone else, from everyone else. Okay, that if I know this estimate, that's what I should bid. So it's very reminding a little bit that about as if the second price auction, because I have to bid the second highest valuation. I don't know it. What is the second highest valuation? Okay, given that mine is the highest, maybe mine is not the highest, but the theorem, the rule tells me, think as if, forget about if it's true or not, think as if yours is the highest and try to calculate what you believe, given that yours is the highest, my valuation is the highest, what is the valuation, the highest valuations of the remaining bidders? Let's say it's 70, bid 70. You think it's 30, bid 30. Okay? Now let's see how we can compute it. So I take a very specific case and suppose that there are at the beginning two bidders. And it is commonly known that their valuation of the object is any number between 0 to 100 equally likely. It can be 0, it can be 1, it can be 57, it can be any number with the same chance. Namely, every bidder knows his own valuation, that's always, and does not know the valuation of his rival, but he knows that it is a number between 0 and 100, and all numbers there have the same probability to occur. It's called uniform distribution. Everyone has equal probability. How come that I have no idea and I assign to your value to be 12 or 37 the same chance, the same probability? This reflects on the fact that the bidder has no prior information about the taste of his rival. I'm going to the auction and I want to bid. Okay, I see you there, but you are coming from a tribe from South America. I have no idea about your culture, what pictures that you had or what you like, nothing. Then maybe you don't like the picture, 0. Maybe you like it most, 100. Maybe, I have no idea. So I assign to every possible number the same chance, and that is uniform distribution. Okay, so I'm talking about the beliefs are based on uniform distribution. I believe that your valuation is in between 0 to 100, equally likely. You believe that my valuation is in between 0 to 100, equally likely. Everyone believes that everyone else has a valuation in between 0 to 100, but everyone knows his or her own valuation. Maybe my valuation is 60, but I believe yours is in between 0 to 100. Good. So suppose that the bidder has a valuation of 60. How much should he bid? By the above rule, we have to make the following exercise. First, he should assume, correctly or not, technically that his valuation is the highest. In that case, we take all this out. Now, after assuming that mine is the highest, 60, yours is anything in between 0 to 60. Now look, it says you have to estimate the highest among the others, but since there's only one other in this case, it's just what I believe about her valuation. So I believe that it's in between 0 to 60 equally likely. So on average, the expected is the middle point, 30. So what should I believe? But should I bid? If my valuation is 60, half of it 30. Similarly, if my valuation is 80, I should bid 40. But that depends on the fact that I face only one other bidder. And in general, if my valuation is V, I should bid V divided by 2, half of V. So then the expected value of its rival must be 30 and therefore should bid 30. So the bid, if my valuation is 60, should be 30. Similarly, if the bidder valuation is V, it should bid half of V. This is under the assumption that we have only 2 bidders. Suppose next that bidders value the object to be in between A and B, sum A and B. A is a number not between 0 and 100, but between 40 to 135. So this will be the 40, the A, and this will be, let's say, 135, or whatever. But not necessarily from 0. It may be, but maybe not. By the way, this B never plays a role. Why it never plays a role? Because I'm always assuming mine is the highest, so I take all this out. Then a bidder with a valuation V should be the middle, but the middle is A for here and V here, so it's the average. Let's say that this was my valuation is 60 and this is 40. So what should I bid? The middle between 40 to 60, 50. How I find it? Regular average. 40 plus 60 divide by 2 equals 50. So this is the average, namely, I take a weighted, it's here regular average, A over 2 plus V over 2. So I give A the weight of half, and I give V a weight of half. Half of A plus half of V, our average between A and V. Great. Then we understand what to do in case we have 2 bidders. And what happens if we have 3 bidders? Hold on a second. So, suppose next that there are 3 bidders and their valuations are in between 0 and 100, equally likely. A bidder with a valuation of 60, when assuming that his valuation is the highest, knows he has to compute or what is the average of the maximum valuation of the 2. So look, this is B, I don't care about it, okay, this is 100, I don't care, mine is 60. All this is irrelevant because I'm assuming mine is the highest. Let's start from 0. Now I throw 2 numbers, I don't know. I mean the other 2 bidders, let's say one of them here, one of them there. Okay, so I have to take this into account. Now I throw another 2 numbers, a random. Let's say one here, one here. So I take the highest, and I take now, I should take the average of these 2 or more and more and more. Let's say that I do it in many ways, I mean many experiments, throwing at random 2 numbers in between 0 and 60, and every time let's take the highest. It is intuitive and can be easily proven using mathematics that actually the average of all this is you divide the interval 0-60 into 3 as the number of bidders, and the highest will be 2/3 of it, and this will be the highest, and this will be the lowest. So actually we are going to bid the lowest, we don't care. We are talking about the highest of the 2. On average, it may be that the 2 of them by chance are here and here. And this is 60, so this is the highest. But maybe it's here or here. So I have to take average all the time of the highest of them. So it is 2/3 away from 0 to 60. So in that case, I'm going to bid 40. I bid, if my valuation is 60 and n equals 3, I bid 40. If n equals 2, I bid half of it, 30. The more bidders are there, the higher I have to bid. Okay? And I have to take into account the competition. The more there are, I should raise my bid in order to have a good chance of winning. Okay. So if the valuation is not from 0 to 100, but rather if the valuations of the three bidders are in between A and B, equally likely, then what I do, I am looking on A and B. I cut all this because I'm assuming I'm the highest. And therefore, this is, I have to divide it into 3 equal parts and to take 2/3 of it. So, if you like, I have to give 2/3 of my weight to V and 1/3 to A. If you want to do it differently, that is I should bid 1/3 A plus 2/3 V. Why? Because, look here, if you like to do it differently, A and V. So first I have to go up to A. Plus, I did look on this interval and I have to take 2/3. So it's 2/3 of V minus A. What is it? It is negative 2/3 of A and plus A, it's 1/3 A plus 2/3 V. And that's what you have here. So actually, if I have 3 bidders, the end point on the left, A, the minimum possible valuation, I give a weight of 1/3, and to the V I give a bigger weight of 2/3. And what happens if I have 4? I'll give 1 divide by 4 quarter and 3/4 to V. So the more bidders I have, then I move toward V. Let's do it in general. The general case, suppose that there are n bidders and their valuations are commonly known to be in between A and B, equally likely. Then in a first price sealed bid auction, or in a Dutch auction, a bidder with valuation V should bid bidder V what? So I look on all this. This is V, and this is B, and this is A. So I divide the interval in between A and V to n equal parts, and actually I bid, and the highest of all the n minus 1 is this point on average. Okay, so it is n minus 1 interval plus n minus 1 over n intervals. So it's actually A plus the difference between V minus A times n minus 1 divided by n. Okay, so I have to take the difference between V and A, I divide it into n parts, I take n minus 1 part of it. The n minus 1 over n. So this is to say, look here, it's A. First, it's A minus n minus 1 plus n minus 1 over nv minus, actually, what do I have here? Minus a n minus 1 over na. So a minus n minus 1 over na, it is 1 over na plus n minus 1 over nv. And this is it. And actually, this is easy to calculate. Then you give me your v and a, then I tell you, and n, obviously, how many bidders, I tell you how much you should bid. This is under the assumption that we believe about the valuation of each other to be uniform between some A and some B, and that we need another assumption here to say that actually the valuations are independent, statistically independent, which means that my valuation is completely independent from your valuation. That is a strong assumption, because if we both study art in Paris, our valuation will not be completely independent. We develop similar tastes, we took the same courses. Then I cannot say that, I don't know, whatever, let's say I look at a picture and I think that the picture is a bad one. The value close to 0, I don't believe that your valuation is million for that. So because I know you, I know about you, we listen to the same courses, we develop similar or at least correlated tastes. But the assumption for that is that all valuations are independent. Note that this bid is increasing in n. You see, the higher n is, V is more than n. If you like, take a bigger n, then all this goes up. This goes up with n. It becomes bigger, the bid becomes bigger and bigger, the higher is n. So the bid is increasing in n, and it approaches V when n is large. Meaning that if there are sufficiently many bidders, the winner will pay an amount which is very close to V. This will be very close to 0, because I have to divide by 1,000, let's say n 1,000 bidders, and this will be 999 over 1,000, very close to 1, so it will be very close to V. Very close to his valuation, and the seller who has incentive to increase the number of bidders will obtain an amount which is very close to the highest valuation. Why? Suppose my valuation is 70, your valuation is 85, and the other, let's say all the valuations of the other are very small. Who is going to win? The one with the highest V. Look on the formula. Everyone using the same formula, but everyone has different V. So my V is the highest, so that will be the highest, and I will win. Okay, if I win, I am the highest one, he gets something very close to my V, because n minus 1 over n, if there are many bidders, very close to V. So with this we can say that actually the seller of the first price auction, if there are many bidders, gets almost the highest valuation as the highest bid, and therefore he likes to invite as many as possible bidders. Also note that auction is efficient in the sense that the bidder with the highest valuation wins the auction. In what sense it is efficient? Let me say a word here. I'll write it here. Suppose that my valuation V1 is 100 and your valuation is 200. And let's say for some reason I thought that your valuation that you are going to bid, you think that my valuation is low, you don't know that my valuation is 100, and let's say that you, with the highest valuation, you bid, let's say you bid 80, and I decided to bid 90. So this is not efficient, I say. First of all, who wins? The one with the lowest, I win, number one, with the lowest valuation. Number two is this one. In that case, there is a, so first of all, what is my surplus? I'm making 10. I'm ready to pay 100 for that, but I paid only 90. So my payoff is 10. What about you? You lost. You didn't get it, so you get 0. So I'll come to you, okay, and I say, you know what? Why don't you give me, if you give me 120, I'll come to you. Suppose, okay, 2 pays 120 for the object. Okay, 1 won of the object, for the object. What will happen? One will be happy, because if he gets 120, one will net, instead of 10, 120 minus the value of his object, which is 20. So he makes more. Instead of making plus 10, he makes plus 20. And what about bidder number 2 with the highest valuation that made before 0? He gets actually obtains 200 minus the 120 that I offer to bidder 1, which is what? 80, more than 0. So everyone is happier. That means that the previous one was not efficient. This cannot be the case, so there is an arbitrage here. This cannot be the case if the winner is the one with the highest bid, and that's exactly what happens here. So if according to this formula, if V, everyone is using this formula, so the one with the highest V must win. So the highest valuation bidder wins the object, and this is efficient. The object goes to the one that is willing to pay for it the most. Now example, so remember what was the formula? The formula was I bid, if my valuation is V and we have N, I bid 1 over NA plus N minus 1 over N. It's weighted average. Notice that this plus this is 1 times V. So it's an average of A and V, but with weights 1 over N and N minus 1 over N. So what is N? N in our case, 4 bidders, so N is 4. If the valuations are in between 100 and 1000, so A is 100, B is 1000. And let's say that my valuation is 700, so V is 700. I just need to plug it in. The bid, if I have my valuation is 700, is a quarter times 100, A, plus 3/4 times the V, 700. You make the computation, 550. So he has to bid 550. Okay, but for example, if I have 5, okay, if the number of bidders is 5, the bid will go up. If N is 5, B of 700 is 1/6 of 100, 1/5, sorry, we're talking about 5. Plus 4/5, N minus 1 over N times what? 700. So this is 140. So 560 plus 20, 580. So there are more bidders, I have to raise my bid. 580 instead of 550. And if there are 10 bidders, then it will be 1 over 10 times the 100 plus 9 over 10 times the 550. Times the 700. So this is 7630 plus 640. So you see how the bid jumps from 550 to 580 to 640. The higher is the number of bidders. Remark, bidding your valuation, we said it, but I'll repeat, while is a dominant strategy in the ascending open auctions or in the second price sealed bid auction, it is a dominant strategy. Okay, it is opposite a dominated strategy, a non-sensible strategy in the first price auction or in the Dutch auction. They are the same. In the latter two auctions, a bidder guarantees to obtain 0. Why? Because in the latter two auctions I mean Dutch or first price, just think of a first price auction. If I bid my valuation, I make for sure 0. If I don't win, 0. If I win and pay my valuation V, I make V minus V 0. So a bidder guarantees to obtain 0 with this strategy, whether or not he wins the auction. So reduce it. The worst case is 0, but if you win by a chance, you make positive. Better than to make for sure 0. Question, if you are a seller of a piece of antique, would you sell it in a first price auction or second price auction? Look, on one hand, selling by the first price auction, as a seller, I'm getting the highest bid. If it is in the second price auction, I'm getting only the second highest bid. So it seems as if the second price auction is not as good as the first price auction. No, this is not the case. Because when I know that I'm playing in the second price auction, I know that whatever my bid is, I don't pay it. I pay the second highest bid. I have somehow motivated to raise my bid in order to increase the chance of winning the auction, knowing that in any event I'm not going to pay my bid. So it so happened that on average, the second highest bid in a second price auction may be higher than the highest bid in the first price auction. And so you can prove in general that under some assumptions, but in general, quite general environments, a seller is better off selling his antique or whatever in a second price auction than in a first price auction. Since eBay is like second price auction, don't be surprised that many use eBay to sell their object, and they make in the second price auction better than otherwise. Answer, after I told you that, it is true that in a first price auction you will obtain the highest bid, while in the second price auction you will obtain only the second highest bid. But remember, bidders may bid higher in the second price auction since they know that if they win, they only pay the bid below the winning bid, second highest bid. In circumstances where bidders are risk neutral and they simply go by the average and roughly speaking have similar background, together with some other technical assumption, second price auction outperform first price auction for the seller. This is not the case if we are having bidders which are risk averse. We'll talk about it. In circumstances where bidders are risk neutral and have independent valuations, so knowing that my valuation does not give me any hint about your valuation, together with some other technical assumptions, they have to be symmetric. Second price auction and first price auction generate the same revenue for the seller. This result, and doesn't matter, second price auction, first price auction, third price auction, they are all giving the same. But for that, we are talking about the very specific circumstances. This is called the revenue equivalence theorem. Now, after doing all this, I want to move to a very simple environment, completely different than the previous one, and therefore the result will be different. And then I want to tell you what is the main difference. The main difference is that I have the valuation. Everyone knows his or her own valuation, but they know also the valuations of the others. So this typically is not realistic. How do I know what is your value of the picture? Sometimes I may know. But this as an exercise is an important one, also to just see how you grasp well the concept of the Nash equilibrium in that environment. So I'm assuming now that I have n bidders, and maybe 10 bidders, and their valuation is the following. The highest valuation is of bidder number 1, who valued the auction to be V1. The second highest is 2. He valued the auction to V2, which is smaller than V1. And then we go to V3 that may be smaller or equal to V2, etc. The lowest valuation is number n, and her valuation is Vn. So Vn, the bidder number n is indifferent between buying the object and paying Vn or not buying it at all. Because if she have to pay Vn, her surplus is Vn minus Vn is 0. And the same for everyone else. Suppose that these valuations are commonly known. That's a big assumption, but we make it. So all this section that comes from here is only for common known valuations. In particular, every bidder knows not only his valuation, but also the valuations of all other bidders. Okay, let us examine the equilibrium strategies in first, second, and third price auctions with the assumption that bids must be integer numbers. That is to simplify our treatment. So let's start. First, consider 4 bidders, namely n equals 4, whose valuations are what? The first one with the highest bid, the highest valuation, has a valuation of 100. The second highest valuation, 90. The third, 50. The fourth, 40. And the bidders as before, the highest bidder is number 1, second, number 2, etc. Now look on a combination. 95, I am bidding, let's say I am the highest bidder, I'm bidding 95. The second highest bid, 94, even though the value is 90. The third one, 45. And the fourth one, who has the value of 40, bids 35. These bids constitute an equilibrium. Let's check it. Look, first of all, one wins. One obtains 100 minus 95 is 5. 2, it is true that bids 94 over her valuation, but she in any event, she gets 0. She doesn't want to outbid 1, because in order to outbid 1, let's say to put 96, she's going to lose 6. Her valuation, remember, is 90. So, and 1 doesn't want, maybe one thing for sure doesn't want to go to 93. In that case, he's not going to win. Now he makes 5. 100 minus 95, he's the winner. Maybe he wants to go to 94. In that case, he saves 1, because he doesn't pay 95, he pays 94, and he will make 6. However, he will win the object with probability half, because he and number 2 both put a bid of 94, and so we choose one at random. So he doesn't want to do it because he gets 6 with probability half, meaning that on average, on expectation, he makes 3. Now he makes 5. So nobody would like to deviate. For instance, for 3 to deviate, she gets 0. He gets 0. So 3 can, if at all, he may consider to overbid 1 to pay 96 to be the winner, but his valuation is 50. Similar for 4. These bids constitute an equilibrium point, but a non-sensible one. Why? Look on, everyone in a sensible equilibrium of a first price auction, every bidder must bid below his or her valuation. This is good for 1, 3, and 4. But 2 is playing in a crazy way. How come that she plays in a crazy way and still it is an equilibrium? Because she loses. She gets 0. So it doesn't matter for her to bid 94, 93, or 7 for that matter. But so this is certainly a non-sensible strategy. Okay, it is dominated strategy because if she wins by a chance, she will lose money. 94 minus 90 would be a loss of 4. And otherwise, if she doesn't, get 0. So, a better strategy is to, let's bid 80. If I win, I make 10. If I lose, I'm getting 0. So I can only, either getting 0 or positive. And here she gets either 0 or negative. Bidder 2 uses a weakly dominated strategy. We call the weakly dominate, we put now W dash dominated strategy. She can either obtain 0 or lose 4. Bidding any number below her valuation is a better strategy for her, irrespective of what the others are doing. Let's take another example. 90, 88, 45, 35. Now each one is, no one uses a weakly dominated strategy. Why? Because everyone bids below his or her valuation. However, it's not an equilibrium. Why it's not an equilibrium? This is not an equilibrium. Look on bidder 1, he wins. He wins and pays 90. His valuation is 100, he makes 10. However, he's better off deviating from 90 to 89. He will still be the winner, but he will pay $1 less. He will make 11. So if any one of the bidders has incentive to deviate, given that all others do not, that's the Nash equilibrium. I mean, the Nash equilibrium is such that no player has an incentive to deviate, assuming all others stick to their choices. This is not the case in 2. Player 1, bidder 1, has an incentive to reduce his bid from 90 to 89 because it improves his payoff. Better off reducing his bid to 89 and still winning the auction and making 11 instead of 10. Let's look on this one. 88, 87, 45, 43. Everyone is the strategy. No strategy is weakly dominated. From that point of view, it's fine. Actually, player 1 does not want to go. Player 1 is making 12. He doesn't want to reduce it to either 87 or below because he may lose. And everything looks fine except that 2 has an incentive to deviate, because if 2 deviates from 87 to 89, she becomes a winner. Now she gets 0 because she's losing. She's not the winner. And if she deviates to 89, given that all the others stick to their choices, she's going to make 90 minus 89, 1, which is positive, and she could improve upon. So that's great. This is not an equilibrium point, since the bidder 2 is better off outbidding bidder 1 by bidding 89. In this case, her payoff will increase from 0 to 1, so she has an incentive to deviate. Good. More examples. Let's talk about 190, 50, 40. Okay? That's the valuations. Now the bidding, 91, 90, 45, 35. This is an equilibrium. Let's check. 1 wins and make 9. 100 minus 91. 2, there is nothing, I mean, that she doesn't want to overbid 1 by increasing it to 92 or to 91, because her valuation is only 90. So, and 1 doesn't want to go down because he may not win. And if he goes to 89, he loses. If he goes to 90, it is true that he makes 10 instead of 9, but the chance that he's a winner is half. So on average, he will make 5. Now he makes 9. So this is an equilibrium. However, but still nonsensible. Why? Because 2 uses a weakly dominated strategy. Look, if she bids 90, and if she wins, let's say for some reason bidder 1 made a mistake, he put 80. Bidder 2 now wins. How much she makes? She has to pay 90, and the valuation is 90. She makes 0. Okay, if if she doesn't win, what happens? 0. So by bidding 90, she guaranteed to get 0. Let her bid 85. I don't know. So she may not win, but if she wins, she makes 5. Otherwise, 0. It's better than 0 for sure. Again, bidder 2 uses a weakly dominated strategy. She obtains 0 even if she wins, and bid below 90 dominates her bid of 90. Let's say bidding 85, as I say. Example number 5. Oh, this is the one. Okay, look on that. First, bidder 1 bid 90 below 100, 89 below 90. 50, you bid B3 below 50, B4 any number below 40. This is an equilibrium. First of all, 1 makes 10. He doesn't want to go to 89 or below. Below, he will make 0. 89, he will make 11 if he wins, but he wins with probability half. So on average, he makes 5.5. Now he makes 10. 2 has no incentive to outbid B1 to put 91 for sure not, because her valuation 90. But even 90, she doesn't improve. Now she gets 0. With 90 also she gets 0. This is the unique, actually. It's not unique because the bidder 3 and bidder 4 can go any number below 50 and 40. But as for the relevant one, B1 and B2, this is in every equilibrium, sensible equilibrium, it must be. That's the unique outcome for 1 and 2 in a sensible equilibrium. And so this is an equilibrium, and look what happens here. Bidder 1 with the highest valuation actually beats what? The valuation of the second one. And this is general. It's not just these numbers. We'll talk about in a second. And 2 must beat 1 below it, because if she put 2 below, let's say instead of 89 she puts 88, then this guy's incentive to reduce his bid to 89. So actually the only sensible, in any sensible equilibrium, what can matter, can change, is only the bids of 3 and 4. 3 can put 40 or 35 or 29 or 49, and B4 can put any number below 40, as long as the highest bidder, the bidder with the highest valuation, beats the second highest valuation, and the second bidder with the second highest valuation bids 1 less than the bid of bidder 1. This constitutes the unique sensible equilibrium outcome. The outcome is what happens, who wins, how much he or she pays. Okay, 1 wins, he pays 90. And to support it, 2 must bid 1 less. Know that here every bidder bids below his or her valuation. That's why it's sensible. So as we can see, I repeat, bidder 1 beats the valuation of the second highest valuation, namely bidder 1 bids 90, bidder 2 must bid 1 less, 89, and all the others below their valuations. It is sensible, and I want to say that this is the unique sensible equilibrium. It's almost true, okay, except let's go on. Except, look on example 6. Valuations now, everything the same except 2, her valuation is not 90 but 99. So this is actually, it will be more general for all cases where V1 exceeds V2 by exactly 1. But let's look on it. So first of all, the bid that, like before, 99 for bidder 1, bidder 2 bids 98, bidder 3 bids below 50 and 4 below 40. This, as before, constitutes, should be S, but that's fine, a sensible equilibrium outcome, since every bidder bids below his or her valuation. Okay, and you can check it is an equilibrium. However, in this specific case where the difference is 1 between the 2 valuations, between V1 and V2, it is there is another sensible equilibrium. What is the other sensible equilibrium? B1 is 98, like B2. So B1 reduces by 1 and compete with 2, and 2 sticks to her. B2, B3 less than 50, B4 less than 40 as before. In this case, both bidder 1 and 2 will win with probability half, because we have 2 highest winners. We flip a coin. Bidder 1 has no incentive to outbid bidder 2. Let's check. If 1 wins, he obtains 2. 98 he pays and obtains 100, 2. But he obtains 2 only with probability half. Okay, and therefore, on average, on expectation, he makes 1 half times 2. Both bidders 1 and 2 will win with probability half. Bidder 1 has no incentive to outbid 2. Bidder 1 obtains payoff 2 if he wins. and his expected payoff is 2 times half, because the probability of winning is half. So with probability half he makes 0, with probability half he makes 2, the average of 2 and 0 is 1. And if he outbids bidder 2 and bids 99, okay, if he goes now, he deviates to 99, he wins for sure, but he obtains 100 minus 99, which is again 1. So he has no incentive to deviate, and you have 2 equilibrium points. But this is only, I have to emphasize, these 2 equilibrium points only if the difference between, we're talking about integers, and the difference between the 2 valuations is 1. In that case, you have 2 Nash equilibrium. But you should think of the general case, except for that one, is that bidder 1 bids the valuation of bidder 2, which is the second highest valuation. 2 bids, 1 less. Let's look on now the general one. Suppose that V1 is bigger than V2. It can be bigger by 1 or by more than 1. Typically by more than 1. Then, sorry, in a first price auction, every sensible Nash equilibrium, in case the difference is bigger than 1, must be whatever we discussed before. 1 beats the valuation of 2, the second highest valuation, 2 beats 1 less, and everyone beats below the valuation. In this case, how much the seller obtains? The seller obtains V2, because in first price auction the winner is B1, he beats V2, so the seller obtains the second highest valuation. In the very special case where the difference is exactly 1, there are 2 sensible equilibrium. Then the one above, and both of them beats 1 below. So 1 doesn't beat V2, but V2 minus 1, and also B2 beats V2 minus 1, like before. Let me go to the before. 98, 98. So instead of 99, both of them beats 1 less. And this will be also a sensible equilibrium, and because everyone beats below the valuation. In this case, how much the seller obtains doesn't matter if 1 wins or 2 wins. In this case, the seller obtains 1 less. Okay, but this is a very exception case. Really, you should think of the equilibrium that the more general one, where the the bidder with the highest valuation wins with a bid of V2. That's always an equilibrium, a sensible equilibrium. It's only in the case that the difference between the 2 valuations is 1, you have another one. Okay. Every Nash equilibrium, sensible or not, is of the form B1 beats something, B2 beats 1 less, and all the 3 beats. There is an exception, with the exception when the V2 minus V1 is 1. Okay? In that case, but look, it may be the case that I don't say that it must be sensible. If it's sensible, you have above. But if it may not be sensible, in order to have an equilibrium, the difference between bid 1, the bid of 1 and the bid of 2 must be 1, except if V2 minus V1 equals 1. V1 minus V2 is 1. For instance, let's say with our example that V1 equals 100 and V2 equals 90 and V3 equals 50 and V4 equals 40, and let's say 1 bids 96, 2 bids 95, and I don't know, B3 bids something below 95, I don't know, 90, and B4 bids 2, let's say equal to 2. It's not sensible, because 2 bids above her valuation, also 3 bids above his valuation. But it's an equilibrium. Okay, why it's non-sensible? It's an equilibrium. because she doesn't want to outbid him because she will have to pay at least 96 or more, and he doesn't. He makes 4. The valuation is 100, and he doesn't want to go below her to lose, or to even to move from 96 to 95, where instead of 4 he makes 5, but with probability half. So on average is 2.5. Okay, so this is the general Nash equilibrium in the first price auction. So you have the sensible one, and if I'm not limited to the sensible one, I have this one with one exception, that I may have x1, x minus 1 in both. Okay, but this is only if V1 minus V2 equals 1. Otherwise, it's not. I mean, in that case, you always have the 2 bids, 1 below 1. Okay, good. Second price auction. First, recall that in a second price auction, it is weakly dominant strategy of every bidder to bid her or his or her valuation. Remember that. Dr. Siuma, in her talk, she explained it to you that in a second price auction, that it's a dominant strategy, weakly dominant strategy for every bidder to bid his or her valuation. Hence, the only sensible equilibrium is this. 1 bids V1, 2 bids V2, etc. Bn, n bids Vn. Everyone bids his or her valuation. But there are many more non-sensible equilibrium points. Many more non-sensible equilibrium points. Maybe don't be misled here, but there are many more equilibrium, but they are non-sensible. Consider the example above, where the valuation is as before, okay? And let's talk about, let me put it here, V1 100, V2 90, V3 50, V4 40. So everyone except the bidder 1 bid sensibly, because they have to bid in a second price auction their own valuation. Okay, remember, they don't pay, the winner doesn't pay his bid or her bid, but the second highest. This is also an equilibrium with the same outcome. Why? Because one wins and pays 90. You see, in both the first price auction, the second price auction, even in here, even if they are playing B1, that the sensible equilibrium, 1 bids 100, the valuation, 2 bids her valuation 90, 3 50, and 4 bid 40. How much? Who is the winner? 1. How much he pays? 90. So the seller obtains 90, like in the first price auction. So this is also an equilibrium. Why? Because there is no incentive. If you reduce it to 94, you still will pay 90. So as long as you win, player 1 wins, he pays 90. So there's no reason. He doesn't want to go below 90, not to win, because he makes now 100 minus 90, he makes 10. And he can go, instead of 95 to 9,500. It doesn't matter. If he wins, he pays 90. But as it was explained before, this is non-sensible for player 1, because player 1 should bid 100. Is also an equilibrium with the same outcome as the sensible equilibrium, namely bidder 1 wins and pays 90. The other equilibrium points where bidder 2 wins. Obviously non-sensible. The only sensible equilibrium, by the way, if this is the case in the sensible equilibrium, who wins? If you bid your valuation, the winner is the one with the highest valuation. And that's exactly efficiency. Also in the first price auction, remember, in V1 bigger than V2, blah, 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 who wins? Always B1, the bidder 1 wins, except for the case that we say that the difference between V1 and V2 is 1, it so may happen in one equilibrium that with probability half 2 wins. But in any event, the inefficiencies there is very, very small because the difference between V1 and V2 is only 1. Okay. There are other equilibrium points where bidder 2 wins. Let's see. Let's B1 80, B2 105, 350, and B4 equals 40. Again, just to remind you, the valuations are here, 90, 50, and V4 is 40. This is an equilibrium where 2 wins. Why? Because she bids 105, more than anyone else. She is the winner. How much she pays? 80. She's happy. The valuation, her valuation is 90. She bids 80. I mean, she pays 80, the second highest valuation, and she makes 10. She doesn't want to deviate. What about player 1? If bidder 1 outbidder and put 106, he becomes the winner, but he has to pay then 105, and his valuation is 100. What happened here? Actually, both of them. This is an equilibrium, both bidder 1 and bidder 2 play nonsensibly. This is an equilibrium where 2 wins, pays 80, and obtains a payoff of 10. If bidder 1 outbid 2, he will win, but will have to pay 105, more than his valuation. Clearly, this equilibrium is not sensible, since 2 bids above her valuation, and 1 bids below his valuation. If we're talking about the second price auction, the only sensible equilibrium is that every bidder bids his or her own valuation. By the way, this result has nothing, it is true if the valuations are common knowledge or if the valuations are not common knowledge. This is a very general result. Moreover, it will be true if bidders you can check it, if bidders are risk neutral or risk averse, that are hate to take risks, and so the result is very, very general. Okay, I'm talking about the second price auction, and what's nice with it, that it is not open to strategic manipulation, because you don't need to think, you simply bid your valuation. You go to eBay, you look on the item that you want to buy, and then you think very deeply what is the maximum that you are willing to pay for that. Let's say you are willing to pay for that is 200. 200 and a penny, you don't buy it, but up to 200, then what is your optimal bid? You simply put automatic bid, outbid everyone else until 200, and if it comes to 200, I'm out. So that's very simple. You bid, and by the way, if you win, you pay less than 200. Okay, because that is your automatic bid. But let's say that the other one has a valuation. Let's say just the two of you bid for the item, and let's say that you decided to bid up to 200, and the other one decided to bid up to 150. In 150 is out, so it goes up 1, both of them say yes, goes to 2, both of them say yes, 3, 4, 5, at 50, at 150, the bidder with the lowest valuation, he says, I'm out, and then it doesn't continue, because the one that left, you don't need to raise the bid. It's only when somebody is going out, and there are 2, the other one wins. So you actually win the object and pay 150. So this is very, very like the second highest bid. So that's what's very simple, very nice. And in addition, as we mentioned, passing by quickly, the seller obtains in a second price auction at least as much as in the first price auction. But we'll talk about it later. Third price auction. In a third price auction, well, this is really, you know, a big fight, because I don't pay my, if I win, I don't pay my bid, I don't pay the second highest bid, I'm only paid, I'm going to be, to pay only the third highest bid. My God, in that case, I really want to win, and I may put my bid in the roof, because in any event, no matter what is my, how much I put, if I win, I don't pay my bid. I pay only the third highest bid. So this really brings to a very fierce competition. And interestingly enough, as we will make a point, the seller will obtain in equilibrium more than in a first or second price auction. As you could see before, exceptional for one very exceptional case, the seller is in both first price auction and second price auction obtains V2, the second highest valuation. Good. Now let's talk about the third price auction, what's going on. But look, if you put your bid out of the roof, I don't know, let's say the object, your value of the object is 100 and you put 1,000, and if the other two below you, or whatever you think will be below you, they decide they think like you, and they put 1,001 or 1,005. Okay, or sorry, you put 1,000, and let's say they put 950, and the other one put 900. You're the winner, but then you have to pay 900. You're going to lose a lot of money. So on one end, you want to raise your bid to win the auction and to pay only the third highest bid, but you should be afraid that the way you think, others will think, and therefore you end up losing money. But in any event, you can prove that very easily, or quite easily, that in every sensible equilibrium you must bid above, greater or equal to your valuation. Okay? In a sensible equilibrium. There are other equilibrium, non-sensible, where you may bid below that, but it is weakly dominated strategy, BI for player I, to bid below VI. You have to bid at least your VI in every sensible equilibrium. Otherwise, bidding below your VI is weakly dominated strategy. Let's go to our example. 190, 50, 40 devaluations, and consider the following bids. Player 1 bids 100, bidder 2 bids 90, bidder 3 50, bidder 4 40. Okay? Is it an equilibrium? First, who wins? One wins, highest bidder. What about 2? 2 puts her bid 90, but she loses. But how much one pays? You look on the third highest bid is 50. So one wins and pays 50. But then 2 has incentive to outbid 1. If she puts 101, she wins. And then the third highest bid is 50. So she pays only 50, her valuation is 90. She has the incentive to outbid 1. This is not an equilibrium, since 2 is better off outbidding 1, even though 1 put his valuation, she will put more than his valuation. She will then win the object, for the price of 50. Okay, but notice, by the way, you have to understand that in this case, in order for her not to outbid 1, if B3 is not going to bid 50, but rather 90 or more, let's say 90 or 97, then bidder 1 will win, okay? And by the way, if this is the case, he will pay 90 no matter what. Even if 3 put 97, he will the third highest will be 90, okay? And then she doesn't want to go above, because if she goes above and 3 put 90 or 97, she either loses, she's going to lose money or to break even, because if he puts 90, she's indifferent. And therefore, in order to support an equilibrium where 2 doesn't want to deviate, 3 should put higher bid. We'll talk about it. For the same reason, the following combination is not an equilibrium. He puts below 90. Why? She's better. Who's the winner? Bidder 1, 115. She puts a little bit less, 110. Bidder 1 that wins has to pay 60. But then she's better off putting 116 because then she will outbid 1, she will be the winner, she will pay 60. Her valuation is 90. So this is not an equilibrium. We conclude that to support an equilibrium where 1 wins, bidder 3 must bid at least V2, which is 90 in our example. The following combination, let's look, but I want just to remind you, V1 is 100, V2 is 90, V3 is 50, V4 is 40. Who wins? 1. How much he pays? 93. Now she has no incentive to outbid him because then she will have to pay 93. Okay? In that case, this is an equilibrium and sensible one. Why sensible? Everyone bids above his or her valuation. We can change the bid B3 of 3 to any number in between V2 and V1. In our example, in between 90 to 100. Actually, we can put here greater or equal, smaller than equal. So we can put it like this. And the bids will constitute a sensible equilibrium. Let's say that we put, instead of 93, we put 90. So player 1 wins. He pays 90. She doesn't want to outbid 1 because she will get the object for 90 while her valuation is 90. She makes 0 as well. Okay? Now let's put, instead of 90, suppose that he puts 100. Still it is an equilibrium. How much one wins? How much he makes? 0. 100 minus 100. If he deviates and doesn't win, he will get 0. Okay? And now 2 doesn't want obviously to outbid him because she will have to pay 100 if she wins. So everything in between 90 and 100 including will constitute a sensible equilibrium. So here is a general rule. Sensible equilibrium in a third price auction where the valuation is like this is characterized by what? First, each one has to bid at least his or her valuation. B1 must be the highest bidder. He is the highest bidder. We have to modify several places. I'll do it after the talk. The third highest bid is in between V1 and V2, including V1 and V2. The winner is bidder 1, who pays the seller in between V2 and V1 for the object. In a first or second price auction, the seller obtains V2, or even V2 minus 1 in the special case where V1 is bigger than V2 by 1. And now he pays in the third price auction, the seller obtains at least V2 and typically more. He can get any number between V2 and V1. Therefore, for the seller, third price auction is more attractive. By the way, a student of mine, he proved that this result, here our assumption is valuations are common knowledge. This is really not very realistic assumption. It's just to see what's going on and what is the Nash equilibrium in this specific case, to give you more intuition. And actually, the question is if this result is true in a general case. So as I said, a student of mine in his PhD dissertation, he actually proved that the seller obtains in a third price auction more than in the first or second price auction. In the worst case, like the second price auction, V2. but typically more, between V2 and V1, he makes more than, even if the valuations are not common knowledge. I know mine, but I don't know yours. The seller obtains on average more in a third price auction than in a first or second price auction. This is very interesting. I tell you why it's interesting, because I don't see down there all the auctions that we see is online auctions are always a second price auction, and we don't see the third price auction, even though at least the mathematical result suggests that the seller should use a third price auction. So it's about time out there that business people will take it into account and will try to see how it works with a third price auction. I can tell you this, I made some experiments in a class in Tel Aviv University many years ago with a third price auction. It was a killer. Okay, the seller in the third price auction in our experiment, I have to say, it's one experiment, so I cannot draw too much of a conclusion, but it was indicative. I can tell you it was amazing how the result was so robust that the seller in the class got much more than in the first or second price auction. Okay. The idea is, I think that people think less rational in the case of third price auction, because they bid very high, more than they should, just because they know, well, if I win, I don't pay my bid, I don't pay the second highest bid, I only pay the third highest bid, and therefore bids are jumping out of the roof. And who is making the money? The seller that uses the third price auction. Now, can I get any number in between V1 and V2? Yes, in equilibrium, any number in between V2 and V1 can be supported in a sensible equilibrium as the seller's revenue. For instance, let's say that the seller wants to get 99. For instance, sellers obtain the revenue of 99 from the following sensible equilibrium. Okay? So let's say that, again, we have to put it here. V1 is 100. You may forget. V2 is 90. V3 is 50. V4 is 40. So first of all, everyone bids above his or her valuation. Secondly, the winner is 1. How much he pays? The third one, 99. So the seller obtains 99. You want a seller to obtain 98? Put here 98. It's again an equilibrium. The bidder 1 wins. 2 doesn't want to outbid him, because if she wins, she will have to pay 98. Her valuation is only 90. You want to get 97? Okay, put 97. You want for the seller to get 100? Okay, put 100. So in every equilibrium, if you want, you can get in equilibrium every number in between V1 and V2. Good. Finally, note that there are non-sensible equilibrium points where it is not efficient. By the way, let's go back, that's important. B1 is the highest bidder, meaning that it is an efficient auction in a sensible equilibrium. Who wins? The one with the highest valuation. Same thing is for the second price auction and the third price auction. However, let me give you a non-sensible one. So consider the following bid combination. Again, V1 is 100, V2 is 90, V3 is 50, V4 is 40. And here's the combination. One bids only 55. Why? I have no idea. It should bid at least 100 in any sensible. 2 bids more than her valuation, 3 bids more, and 4 bids more. First of all, who is the winner? 2. She bids the highest. How much she pays? This is the highest bid, second highest bid, third highest bid. She pays 55. She's very happy. Her valuation is 90, she pays 55, she makes 35 as a surplus. Now, one doesn't want to outbid her, because if one be outbid her and instead of 55 put 101, and 11, he's going to win. But what will be the third highest bid? He is winning with 111, she with 110, and he with 105. He will have to pay 105, while his valuation is only 100. So here bidder 2 wins and pays 55 to the seller. If one outbid 2, he becomes the winner but has to pay 105 over his valuation. Know that one uses a weakly dominated strategy as he bids below his valuation. Okay? Bidding below the valuation of a bidder is weakly dominated. So in any sensible equilibrium, every bidder should bid in a third price auction at least his or her valuation. Notice something interesting, that that in all, we repeat it, in all 3 auctions, the auctions are efficient. In every sensible equilibrium of the 3 auctions, the auctions are efficient, okay, and the sellers in the first and price auction, when valuations are common knowledge, he obtains the second highest bid. In a third price auction, this is the worst case scenario to get the second highest bid, the second highest valuation, sorry. He can get anything in between second and third. So, and by the way, you can, that is just to, I didn't write it. What happened about 4th price auction, 5th price auction? Doesn't matter. It's exactly, the seller will obtain exactly as in the 3rd price auction. So he will get anything in between V1 and V2. So by jumping to the 4th or 5th or whatever, or be above the 3rd price auction, the seller does not improve upon. Okay, so it's enough to consider just the 3rd price auction. Good. Now let me move to risk-averse bidders. As I told you, as for the 2nd price auction, when you have a dominant strategy, bidders bid their valuation, whether they risk neutral, risk averse. Okay, let me just explain what is risk neutral. If you give me, let's say, a lottery where I can get with probability half nothing, 0, and probability half 100, then on the average, so this is a lottery, how I like the lottery. Let's compare it to getting the middle, $500 for sure. If I'm risk neutral, I don't mind getting, taking the lottery of getting with probability half 0, probability half 1,000, or getting for sure 500. If I'm risk averse, I don't like risk, then I will jump on 500. I may even be willing to get 300 for sure and avoid the risk of not winning and getting 0. So that's a risk averse. What is a risk lover? Well, I prefer a lottery where I'm getting 300, where I'm getting, I prefer the chance of having 1,000 than getting 500 for sure. I really like to take the risk, but to get a large amount if I win the lottery. Las Vegas is full of risk lovers, where they are ready to pay quite a bit, unfair in a sense, amount in order to participate in a lottery that may give you $1 million or $100,000. So they love to take the gamble. Okay, so risk-averse, risk-neutral are just what they look on is the expected payoff, or the money for sure is the same thing for them. Insurance companies are risk-neutral. because they don't care if they lose here, they make here, they look on the average, what they care is the expected amount. And how they make the money, because there are a lot of risk-averse people that are ready to pay premium, more than the fair value, in order to be ensured that if something happened to the car or to the house, and the loss is going to be big, so the insurance company will compensate them. Along the year, most people lose their premium and put a claim against the company and get money from the company much less than they paid during their life. But some of them not, some of them, if there is a total loss or the house getting burned, then you get your money back and you are very happy that you didn't lose it. But that's exactly how the insurance company, from what they live. They live out of the fact that they are risk neutral and they face a lot of risk-averse people. Okay. So as I told you, bidders in a second price auction, whether they are risk lover, risk neutral, risk averse, their dominant strategy is to bid their valuation. So nothing changed for them. What happened in a first price auction? Okay, so let's do it. As a seller, do you wish to confront risk lover, risk neutral, or risk averse bidders? If your answer is risk lover bidders, you are wrong. Risk averse bidders bid more aggressively or put higher bids in a first price auction, or for that matter, Dutch auction is completely equivalent to the first price auction, than risk neutral or risk lover bidders. Okay, the risk lovers say, I take the gamble. I don't need the insurance company. I'll manage. I'm happier to take the gamble and pay the consequences than insure myself. The risk here is not to win the object, okay, to lose the object, or to have a burned house. Okay, that's the risk. This is in contrast to the second price auction, as I said, or English, Japanese, or online auctions, where bidding truthfully, namely your valuation, is a dominant strategy for any type of bidders, irrespective of their risk attitude. As I said, neutral, risk lovers, or risk averse. The second price auction, no problem. About the first price auction, it is different. Assuming that all bidders are risk neutral, together with some other standard assumption, sorry. So in a first price auction, everyone is raising their bid if they are risk averse. Why? If I raise my bid, it is true that I'll get less if I win, but at least I increase my probability to win the object, and therefore I decrease the chance that I lose it. So the tension between bidding higher and therefore making, if I win, less, and bidding higher but increasing the probability of winning, for risk-averse bidders, they prefer to raise their bid above the bids of risk-neutral bidders. Therefore, what one has to do, if you are a seller, if you can bring in risk-averse bidders, you will make more than if you bring risk-neutral bidders. Okay.